Welcome back. I'm continuing our study of functions up close and in detail, and special classes that help us to work computationally and in our reasoning. You might want to watch our previous video on surjective functions before watching this one, since much of the language will be reciprocal versions of that story. Nevertheless, you can start here if you're ready. What I have here is a list of possible files in my computer. At the top, I have the PDF file showing me my Taekwondo moves. I'm at the very beginning, so I'm still learning very basic moves. It's also tax season, so after a bunch of other files, I find my tax files. Each of these gets stored on a computer by some string that tells me where it's located. It's known in computers as the path of the file. What properties does this function have? We can start by abstracting the data types into simple types A and B, and not worry about the details of files and paths, but thinking about the concepts nevertheless. What we can say is that every function is assigned to a unique path. That is, if I save a function with the same file name, it'll simply overwrite the one that was there with the new file. At the end of the day, there'll only be one file in that path. So, what we can guarantee is an equation is satisfied. Our function satisfies the following property. For each possible path, the solution has at most one file. That is, there's only one x of type A that could give us that B. Notice what we're not saying. We're not saying that there is a file in every path. After all, I haven't named a file after every possible string. So, this is a situation which is reciprocal to our surjective example, where we had that there were at least one solution. Here, we don't have to have any solutions at all, but if we have a solution, it is unique. It's the only one. Mathematicians call these functions injective, but you might know them by the name one-to-one. There are two directions we could go from here. First, we could ask what kind of diagram might say the same statements. If we can draw this with a diagram, we'll likely follow through our flowcharts and discover that we've had injective functions in many of the story problems we've been studying. The second one is to explore what happens computationally. Since we have an equation with something about a solution, it's likely that there's some algebra we could do that will help us design what programs we would want to add to our injective functions. So let's see both. Here we have what I claim is an alternative characterization of the injective property. It begins with our function f from a to b, but then it conjures out of the sky a new function, f slash, which goes from b to a. The property this f slash has is that when I apply it to the left of f and then apply it to a, I make no changes whatsoever. It's as if f slash is undoing whatever f was doing to the value a. It is a left inverse. The existence of a left inverse may not be unique. There could be several choices that we might make. Let's see an example of why a left inverse might exist on our file system. If we think to name the function from files to paths, the natural word to use would be to save the file at that location. And if you can save a file, chances are high you can also open a file. An open function would start with path and return a file. But there's a catch. We aren't assuming that every single path has an associated file. So we'd like to indicate that there could be an error, or we allow ourselves to return a value that is simply indicating there was no file here. I like to put this with a question mark. In programming syntax, these are sometimes called the option or maybe monad, and there's different syntax for that in different programming languages. I'll put some of the examples in the video.
The creation of a left inverse of an injective function calls for a special class of functions known as partial functions. Recall that a function just means symbols. X maps to phi. X here is a variable. Phi is a program. We can optionally name a function, such as with the letter f, or in programming languages after keywords like def. To apply a function, we substitute the variable x with some value, say c. This is often written f of c. The rules for substitution have to be carried out carefully. We've seen that in another video. To write f maps from a to b is simply to document a property of that substitution. When applied to data little a of type big A, then f of a is equal to a data b that has type big B. But there's a loophole. Nothing in the rules of substitution require us to check the types. That's simply a rule that a programming language might provide. So, it is entirely possible that there's other types of data, say C, with data little c, where maybe f of c is still of type b, or maybe not. This calls for a creation of a new data type. Given a type x, maybe x, denoted x to the question mark, means either a term little x of type big X, or a never before used symbol, like the upside down t, which here we'll call air. We say that x has type maybe x. Keen readers will notice this is a data type we've created before, known as the disjoint union. This gives us a way to describe partial functions, which extends our syntax for simple functions. Here we say f maps from C to maybe B whenever given data little c of type big C, f of C has type maybe B. Here's an example of that syntax in the Scala programming language. We see there's a data type called option x instead of maybe. You can create it in one of two ways. Either you have some data little x of type big X, or you have no data at all. To use this on a function, suppose we try to divide two integers. We know that division by 0 should result in no answer. Therefore, when we check that the value to divide by is 0, we return none. That's one of the possible outcomes of this option of float. On the other hand, if we have a non-zero value, then we go ahead and convert that to floating point numbers and divide it, returning some value. When we run this on the program, we see that 8 divided by 4 comes back as some value, in this case 2. However, when we try to divide by 0, it returns none. In the Haskell and Idris style programs, the syntax changes, but the technique is roughly the same. In this programming language, the data type is usually called maybe. Here we convert data of type x into an example just A or nothing. And once more, if we try to divide by something where there is no definition, we just return nothing. In other programming languages like C++ and Java, the style is to use a different way to leave the function, known as exceptions. Here, we can either return through the float channel, returning the actual value of dividing by n, or, if we detect that we're going to create a problem dividing by 0, we leave through the throws channel. It's another way of giving us a disjoint union of outcomes. By whatever syntax, the extension of simple functions to these partial functions allows us to create many more programming opportunities, including left inverses for our injective functions. In time, you may extend this to include more details. You may have errors of various type, error1, error2, and so forth. And these lead to such structures as hlist, hmaps, and dependent pairs. When you see h used in this way, it means heterogeneous, which is a bit of a silly name because it contrasts homogeneous, and both those words start with h. Go figure.
The goal of open is that it should undo whatever saved it, which means that we could write an equation. We would simply apply open after saving and see that we get back the same file. That equation is just articulating our f/f. This is purely notation to remind us of how that function will behave. The actual name might be more descriptive and useful for you and your clients. Nevertheless, it has a mnemonic which might be helpful. When you write this as a fraction, you could think of this as x over x, which equals 1. When you apply 1 to something, it doesn't tend to change it. So it's a good way to remember. But keep in mind, we're not saying that there is such a thing as a fraction. For example, what is 1 over a path? It would be nonsense. Having a left inverse is a powerful way to recognize the injective property. And it could be something we could write into a series of tests of our software, either unit tests or do part of the typing to check with the compiler. Whichever way you choose to use this, you add some power to your computation by observing that it's an injective function. Left inverses are not generally unique. And that contributes to the difficulty of finding a left inverse from a given function. Individual functions do exist that have left inverses by natural reasons, such as open and save. But there are certainly functions that are injective which we would struggle to find even one left inverse for. So keep this as an aspirational goal, not a requirement of computations. There'll be plenty of injective functions for which we struggle to find a left inverse. We simply want to design programs that could possibly let us do that. Finally, let's imagine the diagram language. If we're looking at flowcharts of large complex systems, it might be difficult to spot an injective function. So if we identify the diagrams that match up with injectivity, we might see a head start. Remember, we're dealing with commutative diagrams. Any two paths that start and end at the same place are a hidden equation. I'm starting out with f copied twice. The reason I want f twice is because I want to think of the fact that there's at most one solution. If I didn't think there was more than one solution, I might have two solutions. So what I'm going to do is create two solutions and then show that they had to be one. I've now created two functions that start from the same place and end at the same place. So there's a hidden equation. I think of it as f composed with u equals f composed with v. Going this way is the same as going that way. Now, because I want to work with this as an algebra, it'll be convenient to stop writing this circle as composition and simply write these as f times u. Now, what would you do if you had to do algebra where you had fu equals fv and you wanted to know something about u and v? You might be tempted to divide by f. Now we can't divide by f, but we do have a left inverse. Let's apply that. First, I notice that f slash f of u is equal to u. That's this left inverse condition. The same thing applies on the other side. Taken all together, I start with u and I end with u. It turns out, if I was ever able to make this square commute, starting from u going through f, or starting from b and going to f, then it would only have been possible if I actually had u and v being the exact same function to start with. This is the way that I can recognize the injective property inside of large commutative diagrams. It's with this cancellation property on the left. If you look back at our video on surjectivity, you'll see the dual version. It was cancellation on the right. We had right inverses. Altogether, we have three ways to think of the surjective property. We can think of functions from a to b, such that f of x equals b has at most one solution. Or we can think of functions that have left inverses. Alternatively, we can start with a commutative square that ends with f on both sides. Then we cancel that and discover that u and v had to be equal all along. Whichever way you think of injective, you'll be stronger if you cycle through these three different modes. There's a fourth property that we can observe from this. If we think of a and b as being sets, then we saw already that sets had a concept of size. And if we think about solving the equation f of x equals b with at most one solution from a, then we can see that the size of b has to be at least as large as a, because while some solutions may not exist, every time there is a solution, then it must be that there's a corresponding value in b for that particular value of a. So, to have an injective function, it would be necessary to have that the size of a is less than or equal to the size of b. Recall we call the size of a set the cardinality. The cardinality of a is less than or equal to b whenever we have an injective function. Depending on the kind of set theory that you build, you can also prove the reverse. If the size of a is less than or equal to the size of b, then there must be an injective function from a to b. Thus, we see that the existence of functions of various kinds are giving us insights into the models we use as well. That is, how big are our data sets? Which property of injective is most important will depend on the problem you're trying to solve. If we think about this in a real story problem, we can start to see that this could help us plan ahead. For example, if we're trying to map web pages to URLs, we see that the number of URLs, those are digital numbers that record web pages, has to be at least as big as we project the number of web pages to someday be. If that number is too small, we can't use it. But we want to engineer this well. We don't want B to be so large that we're wasting a lot of memory every time we allocate a web page. These are the kinds of ways that injectivity can help us study and plan for our problems. So whether you're on the planning phase of a program, or you're designing an API, or you're simply trying to understand the way that data flows through a flowchart, you will benefit from understanding when functions are injective. Do they have a left inverse? Do they have cancellation on the left? Do they have at most one solution to f of x equals b? Pair this with your surjectivity and you'll have a powerful weapon. In fact, in our next video, we'll do exactly that. We'll ask for functions that are both injective and surjective, and we'll see that these have inverses that are extremely strong, but they're also rather rare. Until next time. That's how you take care of your chalkboard.